Okay, yeah. So as I was saying, we're going to just summarize what we looked at or studied all over the semester, do some high-level review of the most important points, but we're not going to. We don't have time to review all the topics, and go through some practicalities regarding the exam, and also hopefully we'll try to keep the second half of the lecture to look at the sample exam from last year. So if we are to think about the problems that we dealt with this semester, we can group them in different types of problems depending on what kind of observations or what kind of data structures we are working with. And the first type of problems are these problems that were about how to actually model the similarity relations between point-wise observations and how to represent and predict group membership. So what we mean by this is our focus, our data point was our sort of our focus was a single data point. So if you remember the vector space model representations and the semantic similarities, we were concerned with one point at a time, one data point at a time, which is one word at a time. So comparing two words, how similar they are, etc. And the same can be said about classification. Again, we were classifying one data point at a time, and therefore the sort of the highlight on point-wise observations. So we're looking at observations in isolation in a sense, even though we take the context as features, but still our focus is one data point at a time. And then from there, we moved into sequences. So instead of just looking at one data point, we were looking at a sequence of data points. When I say data points, in our case, in our course, these were words, right? And the sequences were strings or sentences. So in sequence representation was first introduced in language models. So when we sort of try to predict the probability of a sentence, and there we introduced this notion of a probability over a string. How likely is a sentence? That was the n-gram models. And we call them linear models here. Linear in the sense that the data structure is linear, not in the sense of linear separability that is in classification. The data structure is linear in contrast to what we looked at recently, the trees, the hierarchical data structures. So these are linear, but they are still focused on the surface form. So everything we learned, these models were learned, the parameters were learned in the language models based only on the surface form information, the information that is available in the textual data that we had. And then from there we moved to sequence classification, and that's where we added this abstract layer, this hidden layer of information. And in our case, again, that was the lexical categories or parts of speech tags, verbs, nouns, adjectives, etc. And we used hidden Markov models to represent these hidden sequences. Again, here we're still talking about sequences. So again, our data structure is linear in the sense that it's just a sequence. So we have a sequence of observations and a corresponding sequence of states. And afterwards, we moved into a more sophisticated, maybe, representation, which is the hierarchical structures, the syntactic analysis that was the topic of the last three lectures. So there our focus was how to build a syntactic structure, how to predict a syntactic structure for a sentence. And we looked at this problem from 2 points of view, the declarative and the procedural. So the declarative was basically just defining the production rules, the grammar rules that sort of make up a language. But the procedural is how to actually find this structure, a parsing strategy. How do you find this structure given an observation sequence and a grammar that was defined? And last week, we added a probability notion to our syntactic analysis, which would give us the most likely structure. So by assigning probabilities to the different rules in our grammar, we can compute a score for a syntactic tree by multiplying these probabilities. So all of these different topics might seem as they are separate. So you might feel that they are different dots in this space, but they are actually forming one picture. So that's what we are trying to do here, is to connect these dots to see what are the commonalities, what are the parallels in these different topics, and sort of reflect on them. So you might already have sensed this. You might already have seen that these are not just random topics. These are connected. You can form a pipeline of tasks that is based on what we have learned in natural language processing. And there are many ways also in which we can see this full narrative. So one way is to think about these. All of the methods and approaches that we used were data-driven, right? So we were always starting from some data set and using a machine learning model or algorithm to learn or to uncover the hidden or not hidden and maybe the implicit patterns and rules within the data. So if we think of language models, for example, and we have a data set of textual files where we just collect probabilities and frequencies from these files. What we are trying to do is to learn how these words hang together. So our output is not a pattern or a rule, but still it's a probability that in a way hints to some patterns in the language. So that's where data-driven sort of comes into the picture. And in all cases, what we were doing, we're counting observations, right? So we're just looking at how many times a word occurs with another one, or a part speech tag occurs with another one, etc. So all of these cases were just counting. And the difference was in how we actually choose the context. So that's where the different methods they differ in many ways, but that's if we put them on this sort of on this set of dimensions here, they will differ in how we define the context. So if you remember in semantic spaces, the feature vectors there, the context was defined at one point as bag of words, at least in our assignment. So all words that are occurring in the same sentence with a target word would be features. And that's how we define the context. In a language model, the context was defined as the n-1 preceding words, so the prefix of a given word, n-1 prefix of a given word. In a hidden Markov model, the context was defined on the states sequence. So you remember we had transition probabilities and emission probabilities, and these transition probabilities were corresponding to the transitions between the states. And there we had a sort of a context that's very similar, actually identical to the way we define it in language models, basically the n-1 states. And most recently in PCFGs and probabilistic context-free grammars, the context was defined as the local subtree. So a local subtree of depth 1. So we're given a node, and its context is it will be its immediate children, and that's it. We don't go further down into the tree. So these are different ways of defining context. Another way to look at our topics, sort of the topics that we introduced, is they are all sort of abstract models that we use to represent or conceptualize a problem. So in vector space models, we wanted to find a way, an abstract model to represent the distribution of words or objects in general and how similar or dissimilar they are. The same is with hidden Markov models or graphical, etc. models. And in all cases, we introduced these abstract models, and we also tried to, or we actually implemented them in a sort of concrete way. So we had to do this mapping from abstract to data structures. So that's also a similar or commonality between all the topics that we had. And in this case, when we had to implement all of these models, we had to think carefully, and we asked you to think carefully about the choice of the data structure that you use to represent transitions, for example, transition probabilities, etc. And this should serve as sort of a very clear and first-hand experience for you on the importance of the choice of the data structure. So a hands-on experience with how you actually choose the data structures for different models that are modern and they're still in use. The size of the data sets that we provided you with could have been considered maybe a few years ago large-scale data sets, so 1,000,000 words. It's by no means large scale in today's numbers. So, but still, it's not a trivial data set. So, you were asked to implement hidden Markov models or sort of do parts of speech tagging with a data set that a few years ago was considered the state of the art. So 5 years ago, maybe. Yes, that's common Lisp. So that's you didn't have a choice. You actually were not forced, but sort of we're not presented with other choices to do your obligatory assignments. From my point of view, I think it's a very good experience, even though you might have struggled in the beginning learning Lisp, but sort of you should be reassured by now that you can easily learn a new programming language, and you can, I mean, you wrote programs that are sort of that go in depth in what we are doing, so very well done. And if you use it or not in the future, I don't know, but it's good to know that you can still learn very quickly. And I think if Stefan were here, he would have presented much more, many more arguments on the performance level of Lisp. I won't go into details of that. We're done with it. I think the burning question for all of you now, or most of you now, maybe many of you now, is how much Lisp do you need to know for the exam, since you're done with the assignments? And that's a tricky question, because I mean, we do expect you to know how to sort of write a function in Lisp, but we will not care about the naming of the functions, for example. So we will not care whether you use a function that is called something and then you wrote completely something different. We care about data structures, for example. So we expect you to know the difference between the data structures, the lookup time, how much memory you use, the sort of the preferences, all of these, because all of these were part of the sort of the teaching process. So how to choose the data structures. But we're not going to count parentheses or anything, and we're not going to ask a very, very sort of the smallest proportion of the exam will be on Lisp, but there will be a Lisp-related question in the sense that it is going to be part of the larger picture. So if you look at last year's exam, if you have looked at last year's exam, we asked a part of the question was related to Lisp only, a small part, but then the other part was on the different data structures that you could utilize in Lisp to implement a hidden Markov model, or etc. So yeah, but don't stress a lot about the Lisp part, because we're not going to ask you about the fine details of all of these syntactic sides or aspects of Lisp. Just a quick reminder of what's, I mean, we sort of said that Lisp is a functional programming language. We didn't follow a pure functional programming paradigm, in the sense that we allowed our functions to have side effects. We didn't limit ourselves to recursion, etc. But we all know by now that functions are treated as first-class citizens or objects in Lisp. So you can pass on a function to a function, return a function, etc. We looked at different ways of implementing procedures, the recursive and recursive way, iterative, etc. And yeah, as I just said, since we have actually worked with the data structures, and sort of that was a big proportion of our obligatory assignments, you know them by now, and you should be fine for. Okay, so I'm going to do a quick wrap up. So what will try to do is finish everything before the break. So I might have to rush through some of these, but it's just a quick refresher, so you can actually work through the sample exam after the break. So vector space models, these were data representation models that were based on this spatial metaphor or geometrical metaphor. So we didn't introduce any probabilistic notion to this, so it was just pure counting. And an object in the space is represented as a feature vector that is sort of positioned in a coordinate system. So a high dimensional space where each object will be a point, or sort of a point in this space, and in concrete term, the vector is represented as an ordered set of numbers. Each number will correspond to the value of this object on one of the dimensions. So three-dimensional space, for each feature vector will have a vector of three components. Each of these three components correspond to the value on one of the three dimensions. A semantic space was a vector space models where we utilize this distributional lexical semantics hypothesis to represent the meanings of words and the similarity between these different words. So we introduced the distributional hypothesis, which is you shall know a word by the company it keeps. So if two words have similar context, they are expected to have similar meanings. We had to look at different ways of how to define the context or the feature, bag of words, n-grams, grammatically motivated features, or n-grams based on grammatical relations. We briefly also looked at the effect of text normalization. So in addition to tokenization and downcasing and stripping away punctuations and sort of removing stop words, etc., we also looked a little, or discussed lemmatization and stemming and how they can affect our the performance of the model in terms of getting more sensible representation, but also in reducing the size of the vocabulary. So a word that is like writing, writes, and write would be transformed back into one form and would be represented by just one word, because the assumption here is that all of these forms are so these differences are important for morphology, but not so much in this case for semantics. We also considered different ways of measuring similarity. So we said that similarity in this representation amounts to spatial distance, and we introduced two ways of computing this spatial distance: the Euclidean distance and the cosine similarity, which computes the angles between the vectors. In conjunction with the Euclidean distance, we looked at how the frequency actually affects the measure itself. So there will be a length bias or a frequency bias for very frequent words. So to remedy this problem, to solve this problem, we introduced the concept of length normalization, which transforms all vectors in the space into the unit vector. And one thing that we have seen in theory and in implementation is that these semantic spaces or vector space models tend to be high dimensional sparse spaces. And by sparse, we mean that there will be many inactive features, many zeros in our matrix, or few active features. And that had consequences on our choice of the data structure. From there, we moved into two categorization tasks in machine learning: classification and clustering. In both cases, we were still sort of working within the realm of vector space models. So our representations were based on a vector space representation. And we introduced two algorithms for classification and one for clustering. So, and very quickly, so again, classification is an instance of supervised learning where we have, or we assume the existence of labeled training data. So, and our goal is to learn the representation of different classes. And when we are given a new object, a new unseen object, our goal is to predict the membership of this object, to which class it belongs. In clustering, on the other hand, clustering is an instance of unsupervised learning, which means we don't have labeled data, so we start from unlabeled data, and our goal is to find an optimal formation or partitioning of the space. So this automatically forming groups of similar objects. Yeah, so there is no predefined classes in clustering. All we did is to specify a similarity measure. In both cases, we were relying on the contiguity hypothesis, meaning that objects that are similar tend to be positioned more or less in the similar region in the space. Yeah, so common issues between clustering and classification: how to actually measure similarity between objects, how to represent classes or clusters, and how to represent class membership and or cluster membership. So again, yeah, as I said, in classification we looked at two classifiers, Rocchio and KNN, and if we are to just list the differences between these two classifiers, there are many, but so first of all, Rocchio is a centroid-based or a prototype-based classifier, meaning that for each class we compute a what we call a representative, so a centroid in this case, an average of all the members of one class to be a representative of the class, and K and N and K nearest neighbors. We have what we call an exemplar-based classifier, where each and every member in a class is a representative of this class. And this meant that in KNN there is actually no learning happening, so all what we're doing is memorizing the different instances. Whereas in centroid we computed whereas in Rocchio we computed different centroids of the classes. Rocchio was a linear classifier, so meaning that it assumes that the data is linearly separable, and linearly separable data, if you remember, was if you're thinking in two-dimensional space, is it possible to draw a line that separates the points belonging to class A from the points belonging to class B? KNN is a nonlinear classifier. It has a nonlinear decision boundary. This decision boundary is based on the local distribution of KNN of the members of the different classes. Rocchio makes assumptions about the distribution of the class in order for if you expect Rocchio to work properly, then these assumptions must be or should be met, such as, for example, that the classes should be distributed in a spherical shape and the different classes should have more or less the same size, and etc., and they can't be disjoint or have different regions in the space. In terms of complexity, so one algorithm, which is Rocchio in this case, has a higher complexity during the training phase because we had to compute the centroids, but in the prediction phase it was linear to the number of classes, because all what we had to do is compare to the different representatives of the classes we have. Whereas in KNN, since we said that there is no learning happening, and when we are given a new instance to classify, we had to compare with all the different instances that we had in our training data set, the prediction complexity is much higher. It's linear to the number of the number of instances in our training data. So it's not higher in the sort of in the order. Both are linear, but one is linear in terms of the number of classes, the other is linear in terms of the number of training instances. Here we had to start to ask ourselves about evaluation, because so we have different classification models, and these different classification models have different ways of or different parameters, and we wanted an objective way to quantify the performance of our classifier, and that's where we started to discuss evaluation, the different types of data sets, the train, dev, or fine-tuning and test split. How do we methodologically split our data? And also we introduced different metrics, so accuracy, precision, recall, and F-score. And we discussed when when a metric or a measure like accuracy is appropriate to use, or it's good to use, and when you have a balanced distribution of the data. But when you have an imbalanced distribution of the data amongst the classes, accuracy will not be a good choice. When it comes to multi-class evaluation, so in contrast to binary evaluation, classification, sorry, we had to use micro and macro averaging. And micro averaging, we were averaging in precision and recall over all the instances, whereas in macro we were looking at the classes. Precision recall per class. In clustering, we looked at one algorithm only, which is k-means, and we said that clustering could be viewed as an optimization problem, and our optimization function is this within cluster sum of squares, so the distance of the members of one cluster to the centroid of that cluster. We had to run this, so the algorithm was started from a random partitioning of the space, and then we iteratively improved this or optimized this partitioning. And there are many issues related to this, or not issues in the sense like things that we had to think about. So how to initialize, how to sort of start, where to start, and the fact that this algorithm is sensitive to outliers. So if you have an object that is far out in the space, it will pull away the centroid of a cluster. How do we specify the number of clusters if we don't we have unlabeled data and we don't know what is the optimal k, and how we specify the similarity function, etc. So all of these, so classification, clustering, and semantic spaces, were geometric models. So we didn't have any probability distributions there. So starting from language models, we started to think about the probability distribution. And the probability distribution was we expected the model to give us some probability for some elements being in a particular configuration. Meaning that in language model, we expect the model to give us the probability of a sentence or a sequence of words being in a given order. And the same for parts of speech tag, etc. And the different models that we introduced could be used for different purposes. So if you remember, an HMM could be used for prediction of the hidden layer, the sequence of parts of speech tags, but it also can be used as a language model. So with the forward algorithm, you can actually compute the probability of a sentence by summing the probabilities of all the sequences throughout the HMM. So also a PCFG, a parser, can also be used as a language model, in the sense it can give us the probability of a sentence by, again, adding up all the probabilities of the different parsings that are available for the sentence. So our parser gives us different parse trees, and each of these trees will have a probability. If we add up these probabilities, we will have a value for the probability of the sentence, the observation itself. Yeah, again, we will try to sort of group these different probabilistic models and linear and hierarchical. So linear model is, again, in the sense that the structure that we are working with, the data structure that we're working with, is linear. So it is a sequence. Whereas in the hierarchical, it's a tree, like they parse trees, and within the tree there will be dominance relations, again, like parent node and child node, etc. And the three problems that we were trying, or the three instances of the problems that we were trying to model in these probabilistic models were the probability of a string. So what is the most likely string of these two in a speech recognition system? How to recognize speech, how to recognize speech, the most likely tag sequence for flies like an arrow or flies like flowers here, and the most likely syntactic analysis of a sentence, of an ambiguous sentence like this. Where do we attach the prepositional phrase? To sushi or to eat or ate? I won't go into, actually I don't have a lot of time to go into the details, but one thing to highlight here and across these three models, so these are the equations that we used for prediction, the three models, and that in language models, hidden Markov models, and in probabilistic context-free grammars, we were using the chain rule. So the chain rule had a central role in how we defined our our model, how we predicted the probability of a sentence or the joint probability of a sequence, a hidden sequence and a sentence, etc. Another thing that is shared between language models and hidden Markov models is that both they rely on the Markov assumption, the independence assumption, that very briefly said that we can approximate the history by just looking at the most recent history. So instead of just looking at the full history, we look at the past n words or n states. In both hidden Markov models and PCFGs, there is a hidden structure, there's a hidden layer of abstraction that we wanted to predict. In hidden Markov models, that was a sequence of parts of speech tags. In PCFGs, that is the syntactic tree. Also, in the three cases, we used maximum likelihood estimations to also approximate probabilities or to learn probabilities. And maximum likelihood estimation is basically how the way to transform raw frequencies into probabilities by dividing them. The difference or sort of the particular case for each of these models is the context, the conditioning context. So in language models, we were conditioning on the previous n-1 words, and HMMs dependent on whether we're looking at emission probabilities or transition probabilities. In PCFGs, we're conditioning on the left-hand side of a production rule. So the probability of seeing beta 1 to n given alpha, which alpha here will be a category on the left-hand side of a production or a grammar, a rule in our grammar. In the three cases, again, so these probabilistic models, we had to employ some type of algorithms to achieve what we wanted to do. So not so much actually in language models. So in language models, we were not using any algorithm. We were just multiplying probabilities, right? So and the main challenge there was how to represent the language model, how to store and how to do an efficient lookup of the probabilities. Whereas in HMMs and PCFGs, in HMMs we had to use two types of algorithms, so forward algorithm and a Viterbi algorithm to achieve two goals. The first one is to calculate the probability of a string. So there we use the forward algorithm and to calculate the likelihood of a sequence of states. We had to, or to find the most likely sequence of states, we use the Viterbi algorithm. And if you remember the difference, or there are many actually, there are many parallels in between Viterbi and forward algorithm, but the main difference was that one is adding, the other one is looking for the maximum, but also the forward algorithm is not doing backtracking, or it's not following back pointers, because we don't want to produce anything, we just want to assign a probability to an observation, whereas in Viterbi we actually wanted to find the most likely sequence. So we had to follow these back pointers. Both of these algorithms are dynamic programming algorithms, and they rely on this sort of assumption, or actually this feature in a way in our problem, that many sub-problems will be repeated all over, and there is a recursive nature to the problem, so we could actually decompose it into different problems and avoid repeating the same calculations over and over. And the hierarchical space, we introduced the rules, the context-free grammar rules, to recognize whether a string is a valid string or not, if it belongs to some language. And again, in PCFG we calculated a probability of a tree, and we also had to utilize a dynamic programming algorithm. Again, it's actually Viterbi, to find this most likely tree. Yeah, that's just what I said. In both, so we use dynamic programming a lot in the sort of past 5 maybe lectures, and in the past 2 obligatory assignments also. So yeah, I'm not going to. Very quickly again here. So evaluation, we had to introduce different types of metrics of evaluations for linear and hierarchical structures. Accuracy, that we already know, and hierarchical we just focused on parse-eval, but we could also talk about coverage, the ability of a parser to actually build a structure. So sometimes it will just fail, and that's part of but that's not part, I don't think we looked at coverage. Okay, I just I think that was very quick review. I'm not sure if you were following, or I can't even remember what I said. Yeah. Okay, so it was there. Okay. So just to finalize everything that is related to the exam before the break. So the reading list. You're supposed, of course, to read. So the slides are part of what you're supposed to read, but everything that we wrote as or sort of indicated as background reading on the schedule page, on this on our course page, that is required. So that will be part of the exam. The 2 guest lectures are actually not required. So the word embedding lecture by Andre and the other one by Frederick, you're not required to do the readings there. So just in case you didn't know. Also, the model solutions for the exercises are part of the material that you should familiarize yourself with, which, yeah, haven't published the very last model solution. I will do this after the course, after the lecture. So the exam is on the 5th of December. The location, you should find it on your student web, or this you all have access to. Any questions related to the logistics of the exams are, yeah, should be asked to the administration. We're not involved in this part of the course. So in the exam itself, so the questions will be in English, but you are free to answer in English or Norwegian. So When it comes to answering the questions, these are not my sort of, yeah, I'm not sure how to interpret the first one, but so the idea here is that you're expected to write everything that's relevant. So, and so more relevant is more. That is what we mean by more is more. And less irrelevant is also more. So if you get a question that is about vector space models and you don't know something, or you don't know the answer for that exact question, don't write something else. You will not get points for that. Some people do that, or some students do that. Just, here's everything I know. You will find the answer. That's not how it works. So you should aim for high recall and precision, and now you know the definition of recall and precision, so everything that is relevant should be there, and it should be written precisely. Also, just writing out keywords will not gain you any points, but using the proper terminology will impress the graders, so it's good to use the proper terminology. If you know that this is local ambiguity, for example, you should write that out, or this is a chain rule, or blah blah blah, etc. So yeah, so if you see an opportunity to show that you know the terminology in the courses, just do that, seize it and write this terminology. And when you get the exam, you will find the distribution of the points. So each question will have a number of points, all of them summing up to 100. So this will give you a way to strategically decide where to start. That's I can't remember, but there is no specific limit. So it's it follows the distribution of the points. So if in a year we give a very difficult exam, so this means that the grades will be pushed down. So we will have to adjust the difference. So you get F is fail, and then you have the rest up to A are the grades, and depending on the points that we see, we try to follow a natural distribution. It doesn't always work, but I really can't remember now what and I don't think you should be actually worrying about that, the minimum threshold. Yeah, just any other question regarding the exam? Okay, so, and actually, yeah, for those who are not from the University of Oslo, the grading at the university, I think, at least to me, when I didn't do my bachelor here, so it's very impressive. So the way it's done, so each paper, each submission will be graded by 2 examiners, not just one, and they will, when they reach their grades, they will compare, and if there is a large disagreement, this should be resolved before the results are published, and you have so many rights to complain or ask for explanation, etc. So I think that's nice to sort of very advanced. Just if that matters to you, there were 65 students who submitted the first assignment and 50 who submitted the last one. So 15 decided along the way that this is not a course for them, which is in line with the numbers we had before. And a good thing is that actually the 50 who submitted the last assignment qualified for the exam. So we were exceptionally lenient a little bit on the last assignment, because we know it's difficult and this is the last year for the course, etc. So it's practically difficult to actually retake this course next year. You'd be able to retake the exam itself, but not the course. Yeah, I'll stop here. I think this, yeah, you can just you will receive a course evaluation, fill it, it's good, etc. If you want to a relevant course for next semester, it's the search technology. Some of you have taken it, but it relies on the IR book that we have been using. So if you enjoyed that, we recommend this course. After the break, we'll look at the sample exam. We'll choose sort of vote in which questions you want to look at, and work through them together. Thank you. Or we'll see you in 15 minutes.